If two protons are floating in space 1 meter apart, how hard do they push away from each other? This is the electric force and it's way stronger than gravity. Let's have a look. This is Coulomb's law and it was discovered by this guy named Charles in the late 1700s. He figured out that the force between two objects that are charged depends on 1. How much charge each one has, and 2. How far apart they are. Here's the formula. The force is equal to K Q1 Q2 over R squared. What does this mean? F is the magnitude of the electric force, how powerful it is. Q1 and Q2 are the two charges involved. R is the distance between them. And K is a special constant, just like how we have the gravitational constant or the heat constant. This one, you don't have to remember it, but of course this formula and constant are in the free cheat sheet in the description, with this constant being 9 times 10 to the power of 9. And it's got a weird unit, Newton meter squared over C2. This is Coulomb's constant. You don't have to worry about it too much. Let's go through some intuition. So the bigger the charge is, then the stronger the force. The further apart, the weaker the force. And take a look at this, it's radius squared, which means as you get further and further away, it drops off very, very fast. Just like gravity, it's an inverse squared law. So if you double the distance, then the force drops to 1/4. If you triple it, then it becomes 1/9. And it works whether the charges attract or repel. The formula gives the magnitude only, so just a straight number. The direction is handled separately and it depends on the charge's sign, so negative or positive. If the charges are same sign, then the force pushes them apart, which is repulsive. They repel each other. Opposite signs, the force will pull them together. They attract each other. And this is always along the line connecting the two charges. This is where Newton's third law kicks in. Both charges feel the same magnitude of force in opposite directions. Let's go through an example to make some sense of this. You're analyzing this helium ion and it has one electron that's orbiting this nucleus that has two protons. The distance between them is this number here, 6.3 times 10 to the power of negative 11 meters. The question is, what's the magnitude of electric force between the nucleus and the electron? Here's what's physically happening. The electron is negatively charged because it's an electron. So it has a charge of negative 1.6 times 10 to the power of negative 19 C. C being coulombs, which I'll explain soon. And this number here is not some number I pulled out of thin air. If you Google how much charge an electron has, it's this. For the nucleus, it's got two protons. So we'll label this charge of the proton, which is 2, because there's 2, times 1.6 times 10 to the power of negative 19. And this here is a positive value because positive charge. Since they are unlike in sign, so one's negative, one's positive, that means they attract. So the force is going to be pulling them together. Why is this important? Because this is the force that keeps the electron orbiting the nucleus, just like how gravity keeps the moon orbiting the earth. So this electric force keeps the atom stable. But unlike gravity, the electric force is way stronger. It's orders of magnitude stronger. Let's calculate the force using the formula, which is on the free cheat sheet in the description. It's F equals K Q1 Q2 over radius squared. When you plug in your values, so K is a constant, and we have Q1, we have Q2. I'm not going to write it all out. This is a quick problem. We have the radius, we square that. Your answer, when you do all of the solving, is roughly 1.16 times 10 to the power of negative 7 newtons of force. What does this number mean? It seems small, but for subatomic particles, this force is huge. For comparison, the gravitational force between an electron and a proton is about 10 to the power of negative 36 newtons, which is an insane amount smaller. So the electric force dominates everything at the atomic scale. It's what binds atoms together, it forms molecules, and it governs all chemistry. So before we move on to some proper problems, the electric force is a vector, so it has direction. If there's multiple charges acting on a single charge, then you add these forces with vector addition. Kind of like projectile motion, not just the magnitude numbers. You have to break them into their x and y components. And there's a full 90-minute video on exactly how to do that on my channel. If you want, I'll link it in the description. And this is where diagram matters, especially with non-linear setups. There's all this stuff going on and things are flying in different directions. Here's our first example. Imagine 3 charges acting on a line. Find the net force that's acting on this third one. So here's some values. You have Q1, your first charge, Q2, and Q3. With our reference frame, Q1 can be at 0. So x equals 0. Q2 is at 0.2 meters. Q3 is at 0.6 meters. And the amount of charge they have, we will represent with microcoulombs. And the symbol is this. It's just a bit easier than writing proper coulombs. And I want to expose you to some more different symbols and measurements because it's great to know more. And here's the charges. Q1 has a charge of -6 microcoulombs. Q2 has a charge of +3 microcoulombs. And for charge number 3 is -4. So here's the problem. We're going to look at how much net force is being exerted on the third charge from the other 2 charges. We're going to use our Coulomb's law formula, which is K times the charges divided by radius squared. And the approach we'll take is to find first 2 forces. First, the amount of force that Q1 is exerting on Q3. Second, the amount of force that Q2 is exerting on Q3. So let's get started. And of course, the cheat sheet is going to help you a lot because it's going to have every formula we need to solve these problems. So what's the approach? What is exerting forces on Q3? We have the force coming from Q1 and the force coming from Q2. We're finding the net force on Q3 due to these 2 other charges. Step 1, we need to determine the charge signs, which determines direction. Q1 is negative and Q3 is also negative. Because like signs repel, that means Q1, the force that it exerts on Q3, will push it to the right, pushes it away. The second charge has a positive charge, so that means it will attract our Q3, pulling it to the left. So how we're going to treat this is the right force is positive and the left force is negative. That's our convention. And now we have to calculate each of those forces with Coulomb's law, which is K times charges divided by radius squared. K is this constant. K equals 9 times 10 to the power of 9. And we're going to convert microcoulombs into normal coulombs. This is simpler than you think. Q1 becomes 10 to the power of -6 coulombs. And you do the exact same thing for all of the other charges. So all we've done is this. And we've converted it from micro to normal coulombs. So here's our charges, right? We have Q1, Q2, and Q3. We're now ready to solve. First force we're looking for is Q1 on Q3. So how much is it pushing it to the right? We're going to label this force as 1,3. So plugging everything in, 9 times 10 to the power of 9, which is our constant. 6 times 10 to the power of -6, which is the charge of Q1. And then the charge of whatever the second object is, which is Q3. So Q3 has a charge of 4 times 10 to the power of -6, divided by the square distance between them. The distance between them in total is 0.6, which gives us 0.36 after you square it. This comes out as 0.6 newtons of force. So Q1 is pushing Q3 positively in the direction to the right, away with this much force, 0.6. Now, to find how much force is happening on total, we have to find how much of this 0.6 rightward force is being counteracted and opposed by our left side pull from Q2's attraction. Let's use the same formula. We just got to sub in all our numbers again. Okay, now at this point, and I have to explain something. So if you notice the 4 here, I canceled out the negative sign. Why? Because this formula actually takes the absolute value, so it's positive no matter what. When it comes to Coulomb's law, you don't need to care about the signs in the formula. You're solving things. So what's the distance between 2 and 3? It's 0.4 meters. Square that, you get 0.16 meters. And the answer now, so let's set our old answer aside. Force from Q1 on Q3 0.6 newtons. The force of Q2 pulling Q3 toward it to the left, which is to the left, is 0.675 newtons. This is slightly bigger. And the net force, the total amount of force that's acting on this guy is, you just add it up. 0.6 newtons added with 0.675 newtons, you get negative 0.075 newtons. That's the total amount of force, the net force on Q3 coming from electric force, which depends on distance and charge. Coulomb's law. So it's being pulled to the left since it's negative by this amount of force. Now, the thing about this problem was it was on a line. It was on a straight line. There was no upward direction. There was nothing going in a different direction. Everything was straight. So we didn't have to do any vector addition. But that's very important. That's why we're going through a problem just for that. You have 3 charges. You have Q1, which is positive 5 microcoulombs. Your second charge is negative 3. Your third charge is negative 4. Let's draw our axis. So this way is X. Q1 is right here. Q3 is here. Q2 is here. Here's some numbers. So Q1 is 0.5 meters away from Q3. Q2 up here is 0.4 meters away from Q3. Q1 is at an angle of 30 degrees, like that. And here's the problem. Find the net force acting on Q3, so magnitude and direction. So it's not just Here's our plan. We're going to calculate the force from Q1 to Q3 by breaking it into X and Y components. And then we're going to find the force from Q2 to Q3, which is easier because there's only a vertical component. We're going to add up all of the X components and all of the Y components of these forces, and then we will find the net magnitude and the angle. Vector addition is super important in physics. I would say the 3 big ones that you should know: algebra, trig, and vectors. So again, there's a free masterclass on trig and vectors up on the channel. Let's go through step 1, which is Q1 to Q3. How much force is that? Use Coulomb's law. Force equals Coulomb's constant times the absolute value of Q1 times Q3, so that's our 2 charges, divided by the radius squared, or the distance, which in this case is 0.5. We can convert these microcoulomb values into normal coulombs by multiplying them 10 to the power of 6, and we do that for all 3. Now you simply plug. You get your K constant, and if you don't want to memorize this constant, it's on the free cheat sheet in the description. We have Q1, which is 5. We have Q3, which is negative 4. And we have the distance squared, which is 0.5 meters squared. This is 0.72 newtons of force. This force is attractive because Q1 and Q3 have opposite charges, which means that Q1 pulls Q3 toward itself. Now we have to break this force into its components. Since the angle is 30 degrees above the x-axis, then the x component of the force from 1 to 3 is given with the magnitude of force. And the reason why it's negative is because this direction is negative x. So negative force multiplied by cosine of the angle, so 30. And for the y component, it's the same thing. However, this is in the positive y direction, so the force value is positive. And it's the sine component this time. This is the x component, this is the y component, and it's equal. First of all, the x component is negative 0.624 newtons. The y component is positive 0.36 newtons, and we're running out of space here. There we go. Here's our 2 components. Let's set them aside. We'll just label the x1 as 0.624 negative, and the first y component as 0.36 newtons. There we go. So we found the amount of force acting on Q3 coming from Q1, and then we broke it down into its components. How about the other charge, Q2 to Q3? These are both negative charges, which means they repel. And we have the charge values here. So plugging into our formula, we have F. The force of 2 to 3 is the constant times charge of Q2 times charge of Q3 divided by the radius squared. And this is equal to 0.675 newtons. So we don't have to break this into components because there is no x component, it's purely vertical. This is the y component. The x component of this force would be 0. So now we're ready to add up all of this together. We add up all the x and y components separately. So all of the x components, well, there's only one, so this is the total x component. In total, for y components, we just have to add these, which gives you total y as negative 0.315 newtons. Now let's visualize this in case you're a little rusty on vectors. This y component would look something like this. It's negative, so it's downward. And the x component, continuing off this, would look something like this. When you add these together to find the net force vector acting on Q3 from these two other charges, it would be the hypotenuse of this little vector triangle. And the hypotenuse is found with Pythagoras, which is why this formula works. This is a special formula for finding the net force when you know the two components. It's the x total squared plus the y total squared. A squared plus b squared equals c squared, Pythagoras. And this is roughly 0.698 newtons of force. This vector here. It points down and left like that. And if we're wondering why it points down and left when the forces are up here, because remember, Q1 is pulling toward, like that. And Q2 is pushing down because of their charge signs. So this vector, like that, as a resultant, does make sense. How about the angle? The angle is found with this formula, which you might have seen before. It's the inverse tan function. And it's given by the force of the y component. And by the way, it's also absolute value, so it doesn't matter if it's negative. Divided by the force of the x component, which is 0.624. It's roughly 27 degrees. So the angle that it's at is 27 degrees.